you go with 11?
Sure. Okay, so we know that on number 11, the ramp makes an angle of 20 degrees with the horizontal. And it doesn't say anything about friction. In the picture, it looks like a problem where maybe you would have friction, but it doesn't mention it. So we'll just assume that there's zero friction. It mentions friction below. So I guess we'll do it once without friction, and then we'll put friction in at different values. Okay, so to start with A, there's no friction. These two things have different accelerations. So we're going to follow the steps for connected bodies with different accelerations. It doesn't matter which one you isolate first. I guess I'll choose the one on the ramp as the first body. There's a weight force straight down. Oh, one thing that I wanted to mention on the test was a lot of people seemed sort of unsure about the differences in directions between the normal force and the friction force. I saw a lot of cases like this. So I saw a lot of things where, so look, this ramp is at an angle, right? So I saw a lot of people doing things like, so we know that there's a weight force here. And then I saw a lot of people putting a normal force pushing from the ground like this. Okay, but remember that the rule is a pushing force is perpendicular to the surface toward the body. This is not perpendicular to the surface. This is up. Okay, and so to make it perpendicular to the surface, it wouldn't be parallel to that weight force. It would be like this. Okay, I saw a lot of people doing the reverse of that too. I'll just draw it over here for a second. But I saw a lot of people who put the normal force in the right direction, but then they put the weight force parallel to that, like this. And that's not right either. The weight force is always straight down. That's just what gravity does. It doesn't care about ramps or surfaces or anything. It just tries to pull things towards the center of the earth. The normal force is the one that's always perpendicular to the surface. I was fairly lenient on that stuff. I didn't take off a ton of points, but you definitely want to get that straight or it's going to mess up your vector components when you start writing force vectors. Okay. So free body diagram, I'll call this cable force T. So there it is. And before I go to Newton's second law, I'm going to figure out the components of that weight force vector. So here's the coordinate system. And we're going to use this coordinate system for this body on every part of this. Okay, so we're going to be using a coordinate system like this. When we talk about this one, we're going to use a coordinate system, the regular coordinate system. Okay, because it's not on a ramp. The weight force goes straight down. And so to get from the positive x-axis to here, is that more than 270 or less than 270 degrees? Less, that's right. We haven't gotten to the negative y-axis. So theta for this is 270 minus 20, so 250 degrees. And so that weight force vector is 49.05 times the cosine of 250, 49.05 times the sine of 250. And so that comes out to be negative 16.78, negative 46.09. And now I'll go to Newton's second law. So we have the weight force. Oh. Okay. Weight force. Then the normal force is in the positive y direction. The T force is in the positive x direction. And for the first body, so we'll multiply by the mass, but for the first body, we're always just going to represent the acceleration as either a0 or 0a. Which one is it in this case? Does this move along the x or the y-axis? X, so this is a0. And the x equation here says negative 16.78 plus t is equal to 5a. And I'll just set that aside. We'll use that later. We can't use it yet because we have two variables in one equation. And now I'll go to the free body diagram of the hanging mass. That's also 5 kilograms, so the weight force is down at 49.05. The cable force is up, and that is the same value as the other one, so I'll call it T. This one we're using the standard coordinate system, so I'll just go straight into Newton's second law. We have 0, positive T, plus 0, negative 49.05. Is equal to 5 times, and now this is the tricky part. We have to think about the acceleration of the second body. So the positive x-axis is up and to the right. If the first body moves an inch in the positive x direction, what way does the hanging mass go? Down, and that's the negative y. So I'm going to call this 0, negative a. Okay? Any questions about that? The y equation here says t minus 49.05 is equal to negative 5a. And I'll call this my equation 2 star. And now I'm just solving this system of equations. You can do it by substitution. That's kind of the foolproof method. That'll always work. I'm going to do it like this. I'm going to take the negative of everything in the equation star. So that's positive 16.78 minus t is equal to negative 5a. And I'm going to add it to this second equation that says t minus 49.05 is equal to negative 5a. And that makes the t's cancel out, and we get negative 32.27 is equal to negative 10a. Divide both sides by negative 10, and you get that a is 3.227 meters per second squared. We want the, well, it says what's the acceleration of the block. If we wanted the acceleration vector of the sliding block, we would plug this now into our expression for that acceleration. And so we would get that the acceleration vector of the block on the incline is 3.2270. Or in other words, up the ramp at 3.227 meters per second squared. Okay?
Well, how do you know which one to compare the acceleration in the vector to? How do you know
Yeah.
which time to compare to the?
Yeah, which vector to plug it into?
Yeah.
Really, the question has to be specific about that if I'm going to make any, in this case, it just kind of said, what's the acceleration? So either one you plugged it into is fine, but just know for yourself which one you're looking at, Normally, a question like this would say, what's the acceleration vector of the hanging mass or the sliding mass or whatever. But this is the acceleration of the sliding mass. And then part B says, without friction, what's the tension in the cable? So now we can take this 3.227 for A and plug it into any one of these equations we want. So let's say, I'm going to take equation star and rearrange it. So it says T is equal to 5A plus 16.78. And so T is equal to 5 times 3.227 plus 16.78. And that is 32.92 newtons. And then it asks, well, I guess at the end of part A, it asks, is this speeding up or slowing down? Kind of a trick question here. Can we say whether it's speeding up or slowing down? We can't. What bit of information are we missing in order to be able to say that? The velocity vector. If we knew the velocity, we could compare the direction to the acceleration and say that. But what we know is that it's accelerating up the ramp no matter what its velocity is at that instant. Now, once we start talking about calculations with friction, oh, it does say, so it says this for the whole thing. It's moving down the incline. Okay, so if the acceleration is up and the velocity is down, that means that it's slowing down. Okay? So now we're going to do this problem with friction. I think I'll just do it with one coefficient of friction. I guess that's what it has. So we've already figured out all the angles and stuff. I'm going to do it the same way. It doesn't matter what body you choose first. I'm going to choose the one on the left first again. So free body diagram of the sliding block. There's a weight force down of 49.05. There's a cable tension this way. There's a pushing force from the incline this way. And then since the block is sliding down the ramp, the friction force has to be up the ramp. Yep.
Wouldn't it be sliding up the ramp because it says that the velocity of the hanging mass is going down?
Oh, the hanging mass. Dang it. Okay, I did that backwards. So if the hanging mass has a velocity that's down, that means the sliding block has a velocity that's up. And so for part A, this is speeding up. Okay, and now that we have friction, if the velocity is up the ramp, the friction force has to be the opposite direction, so it has to be down the ramp, and the magnitude is 0.5 times this normal force. Okay? The weight force is the same as it was before. So I can go to Newton's second law. And it says negative, so this weight force that just says 49.05 here, that vector is 16.776, negative 46.092. And then we have the cable force T0. The pushing force of 0n. The friction force is in the negative x direction, so that's negative 0.5 times n, 0. And then all that is equal to the mass times the acceleration. This is free to move along the x-axis, so I'll call this A0. Any questions about that? Okay, so this one now, we're going to have to use both of these equations. Remember, in friction problems, the way you always go is the y equation lets you solve for n, and then you plug that n into the x equation. So the y equation here says negative 46.092 plus n is equal to 0. Solve it for n, and you get that n is equal to positive 46.092. And now we'll go to the x equation. And the x equation says negative 16.776 plus t minus 0.5 times this n value that we figured out now, 0.5 times 46.092. Is equal to 5a. And now you can combine these terms into a single constant just to simplify it. So I'll write this as, let's see, so 46.092 times 0.5. And so I get t minus 39.82 is equal to 5a. And that's my first equation. I'll call that equation star. Any questions about the first body? And now I'll go to the second body. The weight force is 49.05. The pulling force from the cable is up with a magnitude of T. Newton's second law says 0, negative 49.05. Because now, remember, we're going back to the standard coordinate system. There's no reason you have to do that, but it makes the math a ton easier. I would be very surprised if anyone didn't use these coordinate systems and still came up with the right answer. You know, it's possible, but it's a lot more tedious. Plus 0t is equal to the mass of 5. And now we have to think about the directions. So if the sliding block moves an inch in the positive x direction, where does the hanging mass go? Yep, an inch down, so just like in the first parts. So this is 0, negative a. And the y equation says negative 49.05 plus t is equal to negative 5a. And now the two boxed equations are our system. I guess I'll do it the same way I did before. I'll go t minus 39.82 is equal to 5a. And then I'll take the negative of this one. So it says negative t plus 49.05 is equal to positive 5a. The t's cancel when you add these together. And you get 9.23 is equal to 10a. And so a is equal to 0.923 meters per second squared. And so then the acceleration of the sliding cart is 0.923 for x, 0 for y. Or up the ramp at 0.923. Okay, now this one, is it speeding up or slowing down? The acceleration is this way. The velocity, we're told, of the sliding block is this way. And so this is still speeding up. But it's not speeding up as much as in the first example where there was no friction. Okay, yep.
Just so you know, in the answer key, it has negative.
Oh,
The algebra came up wrong, so.
okay, thank you. Okay. So yeah, if there's a mistake in the algebra there, sorry about that. You might want to go on, base it off of this one instead. Any questions about that one? Yes?
Where does the negative go on its when you can't split the t's with it?
So what I did is I took the negative of that equation 2 star, and then I just added the two equations together, added the left sides together and added the right sides together. And so we have a positive t and a negative t. You add them and that gives you 0t, so it just goes away. And then you can use anything you want to, I guess, to calculate t. I'm I'm going to use T is equal to 5A plus 39.82. And so that is 44.44 newtons. And so if you compare that to the tension from the first problem, that one was 32.92. So the friction has made the tension in that cable go up. Yep.
Oh wait, why wouldn't we compare the acceleration to the y of the hanging?
Yeah, you can do that too, and you'll get the same answer. So, so let's do it for this one we just did, okay? So if you think of the hanging mass, plug the A value that we got into the vector for the hanging mass, and you get the acceleration vector is 0, negative 9.23. Okay? Or in other words, it's accelerating down at 0.923. Okay? And then the statement of the problem says that the velocity, so this is the acceleration that we just figured out. It says that the velocity of the hanging mass is down. And so again, you get that it's speeding up. Okay. Any other questions about that? Any other homework questions that you'd like to see? Yes. Yeah. So this one's pretty similar, just with a, you don't have to worry about the new coordinate system. You can just use the regular coordinate system for everything. Okay. So I'll start with, like I said, I just always go left to right. It doesn't matter. I don't think about like what's sliding or anything like that when I determine what body to do first. So I'm going to do a free body diagram to start with of the 3 kilogram. So we have a downward force of 29.43 and an upward pulling force that I'll call T. Newton's second law says 0 positive T plus 0 negative 29.43 is equal to the mass. And now for the first body, is this moving along the x-axis or the y-axis?
Y.
Y, so I'm going to call this 0A. The only useful equation is y, and that says T minus 29.43 is equal to 3A. And that's my first equation I'll set aside. And then I'll isolate the sliding body. We're going to start by assuming there's no friction. There's a weight force down. This is 5 kilograms. So 49.05 newtons. There's a pushing force up that I'll call N. And then there's a pulling force from the cable. So parallel to the cable away from the body. And that's the same cable as this one, so it has the same name. Newton's second law says this T force, you can see that's in the negative x direction, so this is negative T0 plus 0, negative 49.05 plus 0n is equal to the mass, 5. And now we have to think about the acceleration. If the hanging mass moves an inch in the positive y direction, which way does that mean the 5 kilogram is moving? An inch in the positive x direction, okay? And so in this case, we're gonna write this as positive A0. Any questions about that? That is usually the point in these problems where the most people make mistakes. The x equation then says negative t is equal to 5a. So that'll be my second useful equation. And now I'm going to solve this system together. So we got t minus 29.43 is equal to 3a. And I'll just add it to this equation. Negative t is equal to 5a. When you add the 1t and the negative 1t, they cancel. And so we get negative 29.43 is equal to 7a. And so A is negative 4.20 meters per second squared. I'll keep one more digit. 4.204 meters per second squared. Yep.
Why 7A? Because isn't it big?
3 plus 5, because 3 plus 5 is equal to 7. Okay, sorry. Thank you. That's very bad mathing. Okay, let me do that again. So 3.679. Okay, now which one do you want to, which one do you want an acceleration vector for? Let's do it for the hanging mass, I suppose. Well, what one does it say? It says the hanging mass is moving down. So let's plug this into the acceleration vector for the hanging mass, which is this one. So the acceleration vector of the hanging mass is 0, negative 3.679. That's the negative y direction, so you could also just write it as a downward vector with a magnitude of 3.679. Okay, and then it says that the velocity is down. We know that the acceleration is down, and so this is speeding up. Any questions about that? Then you can calculate the tension. So T is equal to negative 5 times A. A is negative 3.679. So T ends up positive, which it always should if you have all your directions right and stuff. And you get that T is equal to 18.39 newtons. Okay, so now let's go to, so now let's go to the case where we have friction. I'll start with the hanging mass again. We have the weight force down of 29.43, a cable force up of T. Newton's second law says 0T plus 0, negative 29.43 is equal to 3 times, does this thing move along X or along Y? Y, so 0A. And so the Y equation says T minus 29.43 is equal to 3A. And now I'll do the sliding block. We have a weight force down of 49.05, a pushing force this way that I'll call N. We have a friction force. Which way is this sliding based on the velocity information that's given? Is this sliding to the left or the right? To the left, it says that the hanging mass has a velocity that's down, so this has to be moving to the left. And that means that the friction force is to the right. And it's equal to the coefficient, which I gave as 0.5 times the normal. And then the last thing we have is the cable tension. Newton's second law says negative T0 plus 0N plus 0.5N0 plus the weight force of 0, negative 49.05. So right there, I thought I was done, and I looked over here and I counted the forces. I'm like, I only have 3 of the 4. You know, this free body diagram always has to tell you everything that you're putting over here on the left side. And this is equal to the mass. And now we have to think about the direction of the acceleration. So if the hanging mass moves an inch up, where does the sliding mass have to move? An inch right. I'll assume you said right.
Oh, yeah.
Yeah. So this is going to be A0. It's such an easy spot to make a mistake there. And like I said, I don't take off a ton of points for it or anything, but you'd rather avoid that if you can. And the X equation says negative T plus 0.5 times N is equal to 5A. And so that's my second equation. No, I don't want to do that yet. Since I don't know what N is, I first want to use the Y equation and say N minus 49.05 is equal to 0. So N is equal to 49.05. And now I want to plug this in the X equation. So negative T plus 0.5 times 49.05 is equal to 5A, or negative T plus 24.525 is equal to 5A. And that's my equation 2 star. Any questions about that? Okay, so now it's these two together. I guess I'll just add these two equations. We have t minus 29.43 is equal to 3a. And I'll add that to negative t plus 24.525 is equal to 5a. These cancel. And you get negative 4.905 is equal to 8a. And so A is negative 0.613 meters per second squared. And so the hanging mass acceleration, if you plug this into the acceleration vector for the hanging mass there, it's negative 0.613 or a downward acceleration of 0.613. And so then if the velocity is this way and the acceleration is this way, it means it's speeding up. And if that coefficient of friction got bigger, if the coefficient of friction was 1, you'd actually see a change in the direction of this acceleration. You can see that increasing the friction makes it slow down less and less. Eventually, you'd get to a point where that friction force overcomes the gravity effect, and this system is actually slowing down instead of speeding up. Okay. Okay, well, any other homework questions? The last thing I want to talk about before we go into circular motion is Newton's third law. I've brought it up before, but I want to talk about it in a little more depth. And we'll discuss this in lab, try to get a better sort of intuitive sense of the way it works. You've heard Newton's third law probably described before. It's the one that says for every action, there's an equal and opposite reaction. But mathematically, it's pretty hard to make a lot of sense out of that statement. So that's not the way we're going to think about it. We're going to think about it like this. If objects A and B are in contact, then the force vector on A by B has the same magnitude and the opposite direction as the force on B by A. And I'm just going to write that as this is equal to negative force on B by A. Okay? So, and this is just the end of it. Okay, so what if? Like, let's think of all these what ifs, you know? what if A is an airplane and B is a butterfly? Or what if it's a short, violent collision? Okay, or what if they're both moving in the same direction? You know, are these counterexamples where you know it doesn't quite apply or whatever? And the answer is it's always true. Okay, so if an airplane going Mach 2 hits a butterfly, the force that the airplane applies to the butterfly has the same magnitude as the force the butterfly applies to the airplane. Okay? It's just that airplanes tend to be a lot more able to handle that amount of impact than butterflies do, you know? The butterfly will do very badly in that collision. But have you ever seen like pictures of airplanes that have run into ducks or geese or whatever? Like, these collisions at these high speeds generate a lot of force, and that force obviously like vaporizes a goose or whatever, but it does a ton of damage to an airplane too. So this is what I want to call common misconception number 3. Okay, so first, what are the first 2 common misconceptions? What was the first one? We watched videos on both of these common misconceptions. What was the first one? Yeah, so gravity does not make heavier things fall faster. Sometimes heavier things do fall faster, but it's air resistance related. What was the second one? Yeah, so horizontal motion does not affect falling or vertical motion. And the video I showed was the bullet being dropped and fired. And so this last one is, so what people often think, what people's intuition often tells them, that in a collision, there's a winner and a loser. And they think that the winner applies a bigger force to the loser, you know, than vice versa. What actually happens is the 2 bodies apply the same magnitude of force to each other. That's not to say that there aren't winners and losers in collisions, but it's not the force that determines that. It's other factors that determine how the 2 things react to that force. And so by other factors, let's say mass is often a big one, or contact with surroundings is often a big one. Etc. Things like that determine how the bodies react to that force. Okay, so I have another video I want to show you. This is a video of someone, I assume, on like a space station or something. And the benefit of a person being on a space station to do this is they don't have to be in contact with anything else when the two objects apply forces to each other. So let me show you this video. What? Where'd that video go? Why did they give him that voice? I bet he had a perfectly normal voice. In space. Okay. Okay, so in the case with the ball, he pushed the ball. That meant the ball applied the same force in the opposite direction to him. He didn't accelerate very much. Like you could say he was the winner of that, like, let's call it a collision. He was the winner of that contact, you know? But the only reason he was kind of the winner, that we would think he was the winner of that collision, is because the mass of the ball is so small that if you apply, say that total force was 50 newtons, okay? If you apply 50 newtons of force to a basketball, it accelerates quite a bit. If you apply 50 newtons of force to a 200-pound person, they don't accelerate very much. And so that's what I mean when I say, you know, these other things determine how the bodies react to the force. So now let's think about a case where there's just absolutely clearly in our minds like a winner and a loser of a collision. So think about like a professional baseball player hitting a, you know, hitting a ball really hard, a home run ball, whatever. So the ball comes in, they hit it, and you kind of have this intuitive idea that they have to be applying a bigger force to the ball than vice versa, because one thing you never see is that the ball comes in, they hit it, and they go flying and the ball stays where it is, you know, like that could never happen. So why is it that, say that it's a contact force of, I don't know what it would be, but let's say 5,000 newtons, something big, you know. If it's a contact force of 5,000 newtons on both of them, why does the ball fly 400 feet and they stay right where they are? And the answer really has to do with the masses and the fact that the player's feet are planted in the ground, you know. If you apply 500 newtons of force to a ball that weighs, it's like 1/10 of a kilogram or something, you know, that's going to cause a huge acceleration to the ball. If you apply 5,000 newtons of force to a 200-pound person who's wearing spiked shoes that are anchored into the ground, and the ground obviously is very heavy, there's not going to be much acceleration for that. So whenever two things are in contact, remember that they're applying equal magnitude forces to each other. What determines what happens after the collision are other things besides that force magnitude, okay? And then the one other thing that to think about with baseball, with that baseball analogy is, so did any of you guys play baseball as kids? Well, you probably didn't play with wooden bats, you know? But when I was a kid, back in the Stone Ages, whatever, our bats often were wood, you know? And so you would get broken bats. And in Little League Baseball or whatever, if you get a broken bat, what happens is the ball comes in, the coach hears a funny noise, he taps your bat on the plate or something, here's a rattle and says that bat's broken. Somewhere inside there's like a little hairline fracture. Obviously, in Major League Baseball, the contact forces that they generate with the ball are much, much higher than the contact forces I generated when I was in Little League, you know, with people throwing the ball 40 miles an hour or whatever. And so have you ever seen what happens when someone breaks a bat in Major League Baseball? It doesn't look like that. No coach has to come out and check whether there's a rattle or anything. Most of the time, the bat just absolutely is obliterated. Like shards go everywhere. Sometimes pieces go into the stands, you know? And that's because, I mean, that really shows how as that contact force goes up, it takes a big force that ball applies to a bat to break it into 5 different pieces and make pieces fly all the way out there. In Little League Baseball, those contact forces aren't generated. In Major League Baseball, that ball is applying enough of a force to the bat to do that, you know. So, anybody have any questions about that? We really mathematically, we've already talked about how to deal with Newton's third law. It's in things like those reaction forces using the same letter and the tension forces using the same letter. But we are in lab going to talk a little bit about kind of intuitively understanding how this works. So, okay, that's all.